Hi, everyone. My name is Chris Reed. I'm a senior software engineer at GE Healthcare. My co-author, Evgeny Drapkin, on my team is the chief engineer of compute. He's able to join us virtually today. And we put together a presentation about one way that we can ensure high performance for our UXL Foundation libraries. And specifically, for just under the past year, we've been looking into using the open source velocity benchmarks to evaluate one API performance overhead. So we've heard a lot about SYCL and one API and some of the great features it can bring, code modularity, portability across architectures. And this is very helpful because the time invested into writing your code, developing your application, can be preserved by just compiling to run on all of these different architectures, CPU, GPU, NPUs, FPGAs. But there is one additional thing that comes in with using one API, and that's a little bit of extra overhead compared to the native implementations that are used to run on these different hardwares. So we believe that for broader adoption of one API within the open source community, minimizing this overhead is crucial. And from our different experiments, we found that setting that performance gap at around 10% as a goalpost is a kind of good line to set for broader adoption, especially given the portability that you're also gaining. So minimizing this overhead is something that's a good priority for the SYCL working group as well. Earlier this year at the IWACL conference, the SYCL working group chair, Tom Deacon, presented some priorities for SYCL that they're working on this year. And two of those have to do with reducing latency, right, and minimizing overhead for both queue construction as well as just kernel submission. So with all the great work that's been going into actually reducing this overhead, we also wanted to propose that the community adopts a standardized way to measure this overhead so we can have better conversations across teams, across organizations, right, referencing the same set of benchmarks. So that brings me to the Velocity Benchmark Suite. So the Velocity Benchmarks are an open source collection of benchmarks. There are 16 of them covering a wide range of different compute domains from high performance compute, machine learning, cryptography, data analytics. And each one of these benchmarks has 3 different implementations, a SYCL, CUDA, and HIP implementation. So you can run these across different hardware, or especially with SYCL, right, you can run it on the same hardware as these native implementations to compare the performance between them. All of these individual benchmarks have teams of maintainers that keep them up, and the open source community is also available to help the upkeep with these benchmarks, either by submitting issues on the GitHub page for anything they might encounter, any bugs. And it's also a really great opportunity, we feel like, for the community to add in either some of their own benchmarks that maybe fit a different compute domain than the 16 there, if they feel like there's another representation they'd like to see. And it's also a great opportunity for targeting other hardware than maybe these 3 native implementations can provide. So you have a great set of 16 benchmarks to choose from to create a different native implementation that you can compare with all 3 of the pre-existing ones to check out the performance, see where the overhead is on that device. And one other thing, when we've been evaluating the velocity benchmarks, we've seen good correlation in the trends of our internal benchmarks that we're seeing with velocity results. So we feel like it's a good representative of the benchmarks that organizations may be working with internally that they're not able to openly share data about. You can probably find similar patterns within these velocity benchmarks that you can better bring up the issues and talk about with the greater community. So just to start off, this was our first attempt at building and executing all the velocity benchmarks, both with one API and the native implementation on our hardware. And it was pretty good for a first attempt in our mind. We saw 6 of the benchmarks in the green that had already fallen within our guidelines and even within 5% performance of the native implementation. And we thought it was a really good sign that those benchmarks also kind of crossed a wide range of different compute domains. Half the benchmarks did fall outside of our goalposts that we set, and I'll get a little bit more into our investigation that we did in collaboration with the CodePlay team on those benchmarks. And two of the benchmarks down there had actually faster performance with one API than the native implementation, which isn't necessarily a bad thing, but it kind of raised a flag that we wanted to investigate and make sure that these benchmarks were functionally the same between all three implementations. And again, I think there's a lot of different use cases for these benchmarks. LC0 is a chess engine. EasyWave is a tsunami simulator. I believe you were talking about crypto before. The ETH miner application has the performance for that. So again, we think it's very applicable to all sorts of workloads. So we hope that you could find something in the velocity benchmarks that's similar to what you want to be looking into. So just to kind of isolate the 8 benchmarks here that we wanted to look into initially, we had really great collaboration with the CodePlay team of engineers, and we were able to find several different improvements for the benchmarks after our first look. One good sign was a lot of the benchmarks that you see the blue dots next to just needed some timer adjustments to help better compare across the different implementations. So for a lot of our benchmarks, we like to isolate the performance metrics around the actual execution on the device and not the initialization time. We obviously do think that initialization time should be hopefully very close in performance across the different implementations as well. But for example, for our applications, usually we just initialize once and you send a ton of work to the device over the course of the application. So for us, it's a lot more important for these benchmarks to focus on GPU or any device execution as a whole. For 2 of the benchmarks, we noticed that we needed to use the in-order queue for the SYCL implementation to better match the functionality of the other native implementations. By default, SYCL uses an out-of-order queue, and we needed to adjust that to have a better and more fair comparison to the other 2 frameworks. For about half the benchmarks as well, we also were able to improve the host task overhead through an extension called the enqueue native command extension, which was actually developed off of an adaptive CPP extension. And this essentially allowed us to, again, kind of match the functionality of the other 2 native implementations by getting rid of any unnecessary synchronization in SYCL when we were enqueuing either kernels to do work on or memory copies. So those enqueues were able to be performed asynchronously without being dependent on waiting for what they're enqueuing to finish. And that helped bring the performance in a lot closer to the other implementations. Some more general observations as the velocity benchmarks as a whole. It was a little bit difficult at first for us to set up our environment to run all 16 benchmarks and evaluate. So we think that that could definitely be improved, and I'll have a slide later on with some proposals. Building and running all 16 of these benchmarks manually also took a lot of time for our team. And the benchmarks were also not necessarily standardized across the suite completely. This was a collection of 16 benchmarks that were brought in open source, right, across a wide array of domains. But even the, just the way it output its performance metrics in the logs was different. So we think that kind of having uniformity and knowing what to look for in the logs across all the benchmarks would help as a suite. One other improvement that we'd like to bring up and are looking into is output verification for healthcare. Right, that's one of the first things we look at even before comparing performance. Right, is the output or the image actually correct? And I think around half or more of these benchmarks that it's relevant for do have output verification, but we would like to see that adopted for all the different benchmarks so you can be confident that you're getting the same results across the 3 implementations, and then you can compare the performance. So after those investigations and getting some patches from the CodePlay team, we were able to run with the newer OneAPI 2025.0 toolkit, and we saw really great improvements. We saw 13 out of the 16 benchmarks now in the green within 10% performance for OneAPI to the native implementation. So that was a really great sign. One of the benchmarks up top, just at the time of capturing for this one, we had a little bit of trouble building for OneAPI, but there'll be a slide later where that's resolved. And after adjusting the timers as well to focus more on GPU execution, we did uncover some other bit of separation that was kind of masked by including kind of a longer period of time for the applications. So CUDA-SIFT is one that we followed up and looked into, and we were able to see some resolution in a later build of the LLVM compiler. So you'll see some results on that too. So kind of touching on the velocity benchmark suite as a whole, we think it's a very useful collection of benchmarks, and we think that in order to kind of improve the ease of adoption for the open source community, making a velocity benchmark suite runner with these 3 different sections would really help adoption and just quickness to get this up and running on your hardware. So the first portion would be kind of standardizing a container or a recipe for an image that would have all the velocity suite requirements, right? Maybe you want to come in and just run one of the benchmarks that's relevant to you, that's fine. But if you did want to evaluate all 16 of them, we think it would be really great to kind of have that recipe. And all these parts are something we were developing internally for our own team throughout the process of evaluating this as well. And we think this would be a really great opportunity for open source collaboration where anyone who wants to run these benchmarks on their particular OS, right, could take the recipes that already exist, and if there isn't one already made for their particular package manager or OS, they could contribute a similar recipe to help others get started as well. Another improvement would also be having just an automatic build and run script, right, to execute all the benchmarks. We think this particularly fits in very well for more pipeline builds for teams. So the LLVM compiler, right, which a certain version goes into each OneAPI toolkit release, but the LLVM compiler on GitHub has nightly releases. So in order to detect any bugs or performance anomalies earlier, if you were to run these velocity benchmark suites every single time you had a new version to check, you could pick up on those problems earlier and fix them in hopefully a couple of nightly releases rather than all at once. When a new OneAPI release comes out, you find 5 different things you have to take care of. And lastly, we think that having kind of an automatic scorecard generation template would be very helpful as well. We think that, like was said before, any one team only has access to a certain amount of software, a certain amount of hardware, and a certain amount of time, right? So by having all of the results for the velocity benchmark be collected into a kind of standardized template, it would allow for really easy sharing of data taken on different hardware, taken with different software versions. So everyone in the open source community could contribute to a sort of database that anyone else could reference if they were curious about any one particular architecture. So this is the last set of data that we were able to collect before we had to make this presentation with the OneAPI 2025.1 release. And as you can see here, we had, again, a lot of great results here. 14 of the benchmarks were in the green. There was one benchmark, TSNE, that was a little bit later for us adopting the GPU execution kind of timer adjustment. But since then, we've been able to run TSNE and get that into the green as well, just not in time to put it in the presentation. So I'll say 15 out of 16 of the benchmarks were in the green and had kind of minimal overhead in most cases. The DL-MNIST application is one that we are still evaluating with the team. It's a little bit difficult to have matching functionality between the implementations for this application due to the kind of find algorithm function for each one of the implementations. So not only does that make it very difficult to choose the same algorithm across your implementations, but even run to run with the same implementation, it may think a different algorithm's faster one run compared to the next. So that's something we're still evaluating to see if it makes sense to use for this type of measurement. So just to give a summary of our evaluation, right, I think for our team, we were able to establish a correlation between our internal benchmarks and the velocity benchmarks in both the overhead behavior we were seeing, as well as the impact of the fixes. So many of the fixes and practices we were seeing and implementing to the velocity benchmarks had same good results to our benchmarks. So we hope that that could be another sort of guide to see for your own benchmarks. You could adopt maybe the same ways the velocity benchmarks were implemented. As for the velocity benchmarks as a whole, we believe it is a very helpful tool to move forward with in multiple areas. One, we think it's a great way, especially as the kind of database begins to have a lot more performance data in it. You can demonstrate maturity of one API for adopters. So I think seeing the page with, 14, 15 applications in the green, hopefully that would make everyone feel very good about the minimal overhead added and the portability that you could gain with one API. We also believe that standardizing on these benchmarks would help make communication a lot more efficient across the community, as well as faster resolution and detection of any bugs or performance discrepancies with so many people running the same benchmarks on different hardware and software. We also think it's a great way for implementers to assess their backends that they may be writing for SYCL, because they have a lot of different native implementations and 16 benchmarks to choose from to implement a version that runs on their architecture, and a lot of performance data to compare with. So finally, we propose that the open source community does take a look and adopt the Velocity Benchmark Suite as a standardized way to measure one API efficiency and just performance across platforms. And that's something that we're pushing for the UXL Foundation as well to continue using these benchmarks and making improvements so it's easier for everyone to try this out and adopt it. So before we get to questions, just want to give a really big thank you to the CodePlay team, Rafal, Duncan, Rod, and Rahman. They were a really big help over the past year working on the velocity benchmarks. And to the engineers on my team, Patrick, Coltrane, and Josh, who helped to build these velocity benchmarks, collect all this data. They were a huge help, and we definitely couldn't have done this without them too. So yeah, thank you all very much. And if there's any questions, happy to take them.
Anyone have any questions?
Maybe I missed it. Was there only one platform that you ran this on?
Yes, it was only one hardware platform. I can't tell you which one it was, but yeah, we ran the one API implementation as well as the native implementation to that platform to evaluate the overhead. So.
Okay, great. I will for sure check out your set of benchmarks.
Yeah, thank you very much. And
thanks a lot.
If there's any more questions, we're happy to follow up with either me or the UXL steering committee as well for more specific details.
Probably have a chat afterwards as well. Maybe.
Yep.
I was going to ask about, obviously, G's been around for a long time, and other projects that you've used in the past around kind of benchmarking, performance measuring that you've seen, work effectively or well that we could emulate?
Yeah, absolutely. I think more of the lessons learned for us can be around how to format those performance benchmarks, like I was talking about with some of maybe the improvements to velocity benchmarks, the emphasis on output verification as well. I think a lot of our performance benchmarks, aside from maybe just general stress benchmarks to stress the hardware, are really based around our algorithms, right? And sanitize as much as we need them to be. But I think from what we've been seeing with the velocity benchmarks, especially with the high performance compute in particular, we saw good representation of similar benchmarks that we have for our configurations in there. So we'll certainly keep an eye out, but I think starting off with the formatting, like how we're measuring performance, how we're verifying the results, could be more lessons learned from what we develop.
Okay, thanks.
All right. Thanks, everyone.